Alright, so we saw hash table already in 228 in greater detail. Hash table is a classical example for space-time trade-off. If you forgot about it, we'll quickly review that. So in this course, we'll build upon, so you already saw some applications for hash table in the 228, but we'll see one more application that will build on the earlier material as well as illustrate the space-time trade-off more effectively. And this is actually your second programming assignment, which is due 2 weeks from now. So make sure you focus on this and listen to this carefully. All right. So what is a hash table? A hash table basically is an efficient way of searching for any element in a sequence, say a list or an array. So if you have, say, an array of integers, right? If I want to search for an integer in this array, and this array is an arbitrary array, it's not sorted or anything, it's some random array of integers. So if that's the only thing you are given and you want to search for an element in the array, the only strategy you can apply is like a brute force strategy of starting from the first index. That's a sequential search which you have done earlier, by just going through element by element, starting from the first element until you find the key. If you're able to find it, we can say I found the search key at a specific index and stop the search there. Otherwise, I have to go through the entire array and then say it is not there, right? So think about this problem. If your search key is not there and your array has again a very large number of elements, 1 million, 10 million and all these things, you have to do that many comparisons and then say the search key is not there. Or if your search key is somewhere like at a very high index, you have to still start from index 0, go through sequentially and then find the search key. So that's going to require more comparisons. But you are not going to allocate additional space, right? So you are given this input array and you just want to stay with that and search for the key. So without creating additional space, you want to search for a key and you realize that it takes a lot of time, more comparisons. So you want to reduce the time, the search time it takes. So what we are trying to do here is, if we allocate more space, additional space, that means space in addition to the input array, if we allocate additional space, can we reduce the search time? That's what we try to see, and yes, the answer is yes. By using this hash table approach, we can search for any element more efficiently. Okay. So a hash table requires us to allocate additional space proportional to the input size, because you see you really need to store where these elements are in the array, or be able to find where these elements are in the input array. So the hash table approaches, we have to be given a hash function. So the hash function is of this format, typically the value, whatever you want to represent in the hash table, mod a divisor, which is always a prime integer. Okay, and I said in 228 why we need a prime integer, because only if you use a prime integer as a divisor, we can more efficiently distribute the elements evenly across the hash table. If we use a prime integer, then the elements are less likely to be evenly distributed across the hash table. Okay. So what is the structure of a hash table? So once you decide the divisor, so in general we write the hash function as h of v is v mod m. So m is the divisor. Then the hash table we say is of size m, the divisor. That's the size of the hash table. So the divisor means, if m is a divisor, we can also say the mod value. So mod means the remainder. So the remainder of the division will range anywhere from 0 to m minus 1, right? So if you're dividing anything, say by 10, the remainders are going to be from 0 to 10 minus 1, 0 to 9. If you're dividing any integer by, say, 35, the remainder is going to be anything from 0 to 35 minus 1, which is 0 to 34. So that is something you should know. So if we are dividing here by m, the reminders are going to be from 0 to m minus 1, and these are called the hash values. So hash value for a key, or in this case I wrote it as v, is v mod m. It's called hash value, also called hash index. Okay, because as part of implementation purposes, we are going to implement the hash table as an array of what is called linked list. So in each index of this hash table or this array, we are going to store a linked list. Okay, and so we did the programming assignment in data structures. We are going to use a similar approach. So how we fill up the hash table? So once we have the hash function, we can set up the hash table to be an array of linked list. How many elements in that array depends on the devices. So if it is 7, then the hash table is of size 7. Okay. Then go ahead and start computing the hash value, that is like 45, the key value, mod the 7. That's going to be 3. So that's the reminder. 45 mod 7 and the reminder is 3. Now in 228 I should have shown this, but let me show this again. I think I should have shown this before too. So how to find the remainder using a calculator? So use 45 divided by 3. That's what we want to find. What's the remainder? So so not 3, 45 divided by 7, that's the divisor, right? So 45 divided by 7 is 6.42857, the actual value. Now we want just the remainder. So discard the quotient, so do this minus the quotient, which is 6. This is the fractional part. Multiply this by the divisor, which is 7, and the answer is 3. So that's the remainder. So that means we will index this 45 at the linked list corresponding to index 3. So we'll put that 45 in the linked list there. Now what about 67? 67 divided by 7 is this value. We want just a fraction, the remainder, so minus the quotient 9, this is a fraction. So multiply this by 7, it is 4. So 9 times 7 is 63 and the remainder is 4. So that's what we got. So that means 67 should be at index 4 and in that linked list there. So as you go from index 0 or left to right of this array, you start building this hash table. 89 mod 7 is 5, so 89 is the first element in this list. Then 45, another 45 element in the array. So 45 mod 7 is 3, so you append whatever is there in the linked list, you add the other 45 there. Then 85 mod 7 is 1, so in that list for 1 you add 85. Then 12 mod 7 is 5, so at index 5 you already have 89, so just append to that list 12. So this is how you build the hash table. Now as we can see, if the if the divisor is not carefully chosen, you may end up with all the elements in the array in one linked list, and if that's the case, you are not really doing any optimization. Why I say that? Because let us do one example of searching. If I want to search, say, for whatever element here, say 13, which is down here, right? How do you do with the hash table? Build a hash table and then say, if you want to search for 13, find what is the hash value or hash index. 13 mod 7 is 6. So all you have to do is go to index 6 and search for 13 in the linked list at index 6. And here you see we have to just do two comparisons. 13 is not same as 90, but then you find 13. 13 is same as 13. So you stop and say 13 is there in the original array. We can also decide if an element is not there in the original array. So for example, you want to search for 20. So what you do? Find 20 mod 7. 20 mod 7 is again 6. So go to index 6 and search for 20 in the linked list there. And with just two comparisons, we can say 20 is not there, because if 20 was there in the array when we built the hash table, it should have been put in this linked list corresponding to index 6, and we should have been able to find it when you search for 20. And since we could not find 20 in that linked list, we can say for sure 100% that 20 is not in the input array. So that is how you can efficiently search for any element using a hash table. But of course, as you can see, the additional space required is growing with input size. So if you have n elements, we have to allocate space for that many elements, n elements. So each can, when you implement as a linked list, it could be a single linked list. So each element is part of a node. So you have to have space for n nodes corresponding to the number of elements you're storing. And then also you have to store the index for this array of linked lists, right? So you can say n plus m is the space complexity. But since n is typically the number of elements you want to store is much greater than the divisor m, we can say n plus m is approximately n. So that's why the space complexity for a hash table is written as theta of n. Okay. Now for time complexity, we would like it to be almost constant time, in the sense that if for any array, if the elements are evenly distributed across the array, we want to be able to search in theta of one time complexity. Okay. But of course, as we can see, in reality, we cannot guarantee that we can search in almost constant time. It depends on the divisor. So at the worst case, if most of the elements end up being in one linked list, then we might have to go through the longest of the linked list, and that will be n elements at the worst case. So best case is just like an even number of it doesn't depend on what linked list or what hash index it is. It's the same number of comparisons. That is going to be like all n elements are equally distributed. So that's the best case, minimizing the number of comparisons. The worst case is you may have to go through all the elements. All elements end up being in one linked list. So we can say it is big O of n. That's the time to traverse the entire linked list at the worst case. So that's the time complexity, but we don't really go through that many comparisons all the time. That's the worst case. So the best case is almost theta of 1 time complexity. So that's why for all analysis purposes, we can say the search time complexity for a hash table is theta of 1. But we can achieve such a constant time complexity by allocating additional space. So that's why it's a classical case of space-time trade-off. We cannot achieve a constant time complexity without allocating additional space. Okay. Any question on this about hash tables until this? Okay, we have 10 more minutes. We can go through those two examples out there. All right. So, okay. Let us see some applications of hash table. Not applications, we will see that in next class, but the number of comparisons. Okay. So how to calculate the number of comparisons we did in 228, but we'll just kind of quickly review that to basically again reinforce how we can reduce the number of comparisons on average with the hash table. Alright, so given this array, it's not the same array as this, so it's a different array. And this same hash function v mod 7, so that means once you fix the hash function, pretty much the size of the hash table is fixed. We have 7 elements or index entries in the hash table. So it's an array of linked lists. How many linked lists? 7 linked lists. And so for your assignment, you need to kind of review that implementation code for hash table as an array of linked lists. So that means what we do there, we create an array of linked lists. So each linked list is initialized with what? Just a head node, and the next node following the head node will be null. Okay, that's how we initialize things. And then as you find the hash values, you start inserting the data to those linked lists. Alright, so in this case 45 mod 7 is 3, so 45 will be inserted to the linked list at index 3, and then 23 mod 7 is 2, so we'll insert 23 and then keep going. Alright, so once we build the hash table, we can do some analysis on the number of comparisons. So how to find what is called the average number of comparisons for what is called a successful search. So the search operation, the end result can be either successful or not successful. So you can say it's a successful search or unsuccessful search. So a successful search is a search if for something that is part of the input array. So if the element is in the input array, it's going to be somewhere in this hash table. So if the search element or search key is the first element in any of this linked list, then you're going to require just one comparison, because once you find the hash index, you're going to search in that only in that linked list or that hash index. So if that search key is the first element in any of this linked list, we are going to require just one comparison. If the search key is the second element in any of those linked lists, then we require two comparisons. Okay. Then if it is anywhere the third element in any of those linked lists, we require three comparisons. So now to find the average number of comparisons, we have to just consider how many elements are going to be found as the first element in any of this linked list, how many as second element, and so on. So you see 1, 2, 3 up to 7 elements are going to be as first elements in any of this linked list. So it is 7 times the number of comparisons for any of them is one comparison. Then there are 2 elements that can be the second element in any of those linked lists, so that is 2 times 2 comparisons for each of them. Then there is 1 element that can be the third element in any of those linked lists, and for that we require 3 comparisons, so 1 times 3. So sum these up, divide by the number of elements, so that's 14 divided by 10. So that's like a weighted average. How many elements require 1 comparison, how many requires 2, and so on. So that's 1.4 comparisons on average for a successful search. Now you compare this with how many you would have to do in the case of an array. With an array implementation, for a successful search, you might do 1 comparison if the element is at index 0, or 2 comparisons, then 3 comparisons, and so on. So if you have 10 elements, you may require to do 1 or 2 or 3 up to 10 comparisons, depends on where the search key is. So on average you have to do all these numbers of comparisons and divide by 10. That is n times n plus 1 over 2, which is 10 times 11 over 2, which is 10, which is 5.5. Okay. So with an array implementation of array implementation means you're not really allocating additional space. If you want to search for a key, the number of comparisons you have to do on average is half of the array size, which is n over 2. Whereas the number of comparisons you have to do for a successful search for 10 elements like this is 1.4 with the hash table. So you can see the trade-off again. So if you allocate more space, you can reduce the number of comparisons. Otherwise, you have to spend more comparisons. Now, at the worst case, for a successful search with the hash table, the number of comparisons you would need depends on the longest hash table you have. So in this case, we have a hash table of size with linked list of size 3, right? So that's the longest linked list we have. So at the worst case, we may search for something that is last element in the longest linked list. That, like if you're searching for 30, so that would require 3 comparisons. But on the other hand, in this array example here, if you search for the 30, you will require to do 10 comparisons, basically go through sequentially starting from index 0. Now unsuccessful search, right? With an array, it's always you have to do the max number of comparisons, because an unsuccessful search means you're searching for something that's not there. And with an array based implementation, you have to go through the entire array before declaring the search key is not there. Whereas the hash table based implementation, we can search for, so if you're searching for something that's not there, say for example you're searching for 9, which is not in the given array, you will do 9 mod 7 is index 2. Then you index to cell 2 and search for 9 in that linked list, and basically you will do 3 comparisons and decide 9 is not there. If you're searching for 10, you will say 10 mod 7 is 3, index into this linked list here. Just do one comparison and say 10 is not there. So for unsuccessful search, it depends on again where you index into, and that's the number of comparisons you do, the number of comparisons, the size of that linked list in that index. So at the worst case, you may have to index into an index where the linked list is the longest, like this, if you're searching for 9. And so for the worst case, number of comparisons for unsuccessful search with a hash table is the length of the longest linked list, which is 3. This example here. As an array, you have to do 10 comparisons. This example, just simply the number of elements. So this is an example that illustrates the number of comparisons that you would encounter on average, as well as on the worst case with a hash table, and compared with an array-based approach. Okay. Right. So next time we'll go through this application of hash table. That's your second assignment, and then we'll move on to the next module. Right. So any question? So you have 2 TAs for this course along with the data structures course. So Landry and then another student, Opilova. Both the office hours of both students are posted in Canvas, so you can reach to them during their office hours. It's also virtual office hours, and then you can also reach talk to me after this class for doing my office hours if you have any questions, or you can email us too. Okay, so start working on assignment 1, and let me save this video.